Have you ever watched a robot or move with seemingly effortless grace? Or perhaps seen a mobile robot zip across a factory floor and wondered, what exactly dictates how fast it can go? Robot trajectory speed is primarily influenced by a complex interplay of several key factors, including the robot's physical capabilities, the nature of its task, and the environment in which it operates. Understanding these elements is crucial for optimizing robot performance and safety. At its core, a robot's maximum achievable speed is constrained by its hardware. This includes the power and torque of its motors, the structural rigidity of its links and joints, and the precision of its gearboxes. Each joint has limits on how quickly it can accelerate, decelerate, and reach a certain angular velocity. Over time, pushing these limits too often can lead to wear and tear, reducing the robot's lifespan. The dynamics of the robot, which account for its mass, inertia, and payload, also dictate how much force is required to achieve a desired acceleration or speed. Additionally, the control system's update rate, often called the servo rate, directly affects how precisely and rapidly the robot can react to commands and maintain its planned path. Considering these factors, robotic engineers and programmers often use trajectory generation algorithms to create motion profiles that respect these physical limits. For example, a common approach involves creating a smooth velocity profile for each joint, typically trapezoidal or S-curve, to prevent sudden jerks which could damage the robot or its payload. This process is known as time parameterization, where a geometric path is assigned a specific time, law of motion. Another significant aspect is the presence of singularities, which are configurations where the robot loses one or more degrees of freedom. While not directly affecting maximum speed, approaching a singularity can cause joint velocities to spike to extremely high values to maintain end effector speed, often leading to a slowdown or even a halt to avoid overspeeding the joints. Workspace constraints, such as obstacles or collision zones, also necessitate reducing speed to ensure safe navigation. Furthermore, the payload carried by the robot adds to its effective mass, increasing inertia and requiring more motor torque for the same acceleration, thus often leading to reduced speeds. So, when designing or programming robot movements, it is not just about telling the robot where to go, but how quickly and smoothly it can get there without exceeding its physical boundaries or compromising safety. By carefully considering motor limits, structural integrity, payload, and the geometry of the task space, engineers can create efficient and robust robotic systems that maximize throughput while minimizing stress on the hardware.
If you love robotics, like, subscribe, and keep building with us.